Okay, I've been playing with all these resources. I probably should have shown you this at the beginning of the course, but here we go. I wanted to show you this. Like here's a chalkboard video on problem number 12. Now, did I assign problem number 12? No, but I'm gonna probably start assign. I'm gonna look over here and see what the problems are and start assigning these guys. Um, and so let's call that up.
In this problem, we wish to calculate the speed and centripetal acceleration of a person standing on the equator and compare that to a person standing at theta degrees north latitude. Let's draw a figure to help us visualize the problem. We will assume that the Earth is a perfect sphere and that it rotates once per day around an axis that passes through its north and south poles.
So pick up some of the information
the axis
here.
about which the Earth rotates is actually tilted about 23 degrees from vertical as it revolves around the Sun. For clarity here, we rotate it to vertical since this does not affect the answer to our problem. Notice that one person is standing here at the equator, and thus as the Earth rotates, will move along the circle whose radius is equal to the radius of the Earth, r sub e. The other person is standing at theta degrees north latitude as the Earth rotates. This person will move along the circumference of this circle, which has a radius less than the radius of the Earth. Let's call it s. To calculate the speed that each person moves, we use a relationship from uniform circular motion that relates the period to the speed. Rearranging, we find that the speed is given by 2 pi r divided by the period t. Each person completes his trip around the Earth in the same time. In other words, they each have the same period. And for the Earth, we know this period is equal to 1 day, or 86,400 seconds. Now we can calculate the speed for each person, which will be given by the following. To calculate the speed of the person standing at theta, we need to write s in terms of the radius of the Earth, r sub e. From the figure, we see the following distance also equals the radius of the Earth, and this angle equals theta. Using a little trigonometry, we see that s is equal to r sub e times cosine theta.
Right here.
Substituting this into our equation for the speed of the person standing at the angle theta, and we get our final result. We also want to calculate the centripetal acceleration a sub c at both locations. Recall that the centripetal acceleration
that was kind of
defined
tricky.
as v squared divided by r. For the two locations, then,
that was kind of a tricky little thing. Did you see what they did? So the velocity, little trig, but it's a good problem. But it shows. I'll let him keep going.
We get the following results for the centripetal accelerations. Since we derived expressions for the speeds in the first part of the problem, we can substitute these in to calculate the centripetal acceleration at the two locations. This gives us our final result for the centripetal accelerations in terms of the radius of the Earth, the period, and the angle theta. Notice that the centripetal acceleration for the person standing at theta degrees north latitude depends on cosine theta. Thus, if theta equals 0, which means the person is standing at the equator, then cosine theta equals 1, and the expression becomes equivalent to the one we derived specifically for the person at the equator.
All right, and that has an interesting consequence, actually. So, see, there's a little 2.5 minutes, that explains a problem. And let's look at problem 21. Maybe.
In this problem, we wish to analyze the track and field of
no. This is a great problem, but I'm not gonna do it. I don't think I assigned. Okay, no, they just explained the swing on the carnival. Okay, which is kind of interesting, because of what the carnival at a carnival when you're in one of those swing things that's spinning around and around, and you feel the force. But here's what I wanted to show you real quick. So I'll try and draw my Earth the best I can. Kind of draw this ball, this sphere. Here's the equator coming around front. So if you're standing here, because here's something I want to emphasize very, very strongly. If you're standing here, all right, first of all, you have a force due to gravity. The gravitational force is equal to me times the mass of u divided by re squared, which we know is mg. Okay? So you've got that force going inward. You also have a centripetal force going inward. AC, which we just calculated as R, as that centripetal force is equal to, or the centripetal acceleration is equal to your velocity going around the Earth squared divided by RE. All right. There's also another force, normal force, acting on you. All right. Now the net force in anything where you're going around in uniform circular motion, the net force is always MAC. All right. Want to make sure we know that. So if we take some of the forces in this case in the x direction, the net force is minus MAC, which is equal to Fn minus mg. Okay? Fn minus mg. So therefore, ergo, Fn is equal to mg minus MAC. Which is kind of interesting because that means if you're standing up here, all you feel is mg. Your normal force is equal to mg, and there's no centripetal acceleration pulling you in. I just find that interesting. So you actually lose weight if you go to the equator. If you get going fast enough, if this MAC eventually equals mg, then the normal force becomes zero. The normal force becomes zero. What happens? Whoosh, you go flying off the face of the Earth. All right, probably got too deep there.